Hello, everybody. Okay, so this video is just going to be a little inverse trig review. I have part one put here. I don't know if there's going to be a part two or not. We will see. But let's just jump right in. The first thing is this whole thing about invertibility. So, first of all, inverse, right? Let's just go in functional inverse. That's what I'm talking about. Let me put that in parentheses here. Functional inverse. That's where we take all the x's and y's and flip them around. Okay, so we interchange x and y. X becomes y becomes x. That's what a functional inverse is. And if we remember a function requirement, so this isn't an inverse, this is just in any function in the world. Function requirement is all x's go to only one y. Okay, so any choice of x in the world only has one y value that it goes to. Visually, here's what I'm talking about. Let's see, here's an x value. So if I have this point here, I cannot have this point here. This is the same x value going to two different y's. This is a function violation, not a function. Yeah, I'll just write not a function. How about that? Not a function. That's not a function there because we have the same x going to two different y's. So let's remember that this is a requirement of any function in the world. And now suppose we interchange x and y. Well, let's not do that yet. Let's look at one more thing. Let's look at this now. Let's look at this situation where here these 2 points have different x's, but the same y. Okay, so if we have a curve like this that touches both of these points, this is okay. All right. However, if we take these 2 points and invert them, in other words, if we interchange x and y, then what happens is where the y values used to be identical, if we interchange x and y, then here x is going to be some positive number, and then y is going to have a positive and a negative version, just like here, because look, here x is positive, here x is negative. So here, if we interchange x and y, y is going to be positive, y is going to be negative. But now if you look at this is the inverse. Wow, I cannot spell. I just can't spell at all. This is the inverse of this guy over here. Okay, and so this is also not a function. Okay, so the point is, to be invertible, every x goes to only one y. And let me stop saying goes. I'm going to say every x has only one y. And also, every y has only one x. This is called a one-to-one function. One-to-one function. So a one-to-one function is invertible. Okay. So let's just look at some quick examples here of some curves. So this one that I'm getting ready to draw, this thing is a function. Every x only has one y. But if I choose any y value, if I choose any height, there is more than one x that has the same y value, the same height. Okay? And so this is a function. But non-invertible. This one is not a function. It fails what we call the vertical line test. A vertical line passes through more than one point. So we have x values going to more than one y, not a function. So then finally, something that is invertible and is a function looks kind of like this. Looks kind of like this. Well, we have to cut it off. We have to cut it off here. Yeah. Good. All right. So this thing, and neglect this dip here. There's no dip. There's no dip. It keeps going up. Anyway, so now it passes the vertical line test. Any vertical line only passes through one point, and the same is true for the horizontal line test. Horizontal line only passes through one point. So this is a function, and it is invertible. Okay, good. So now we can finally direct our attention to inverse trig. Okay. So for inverse trig, we have, like we were saying before, we have two notations. We have the -1 notation for functional inverse of sine. And then we have this notation, the arc sine. They're the same thing. Same notation. I'm sorry, different notation for the exact same thing. These are the main ones that are used most frequently. There is an inverse cosecant, inverse secant, inverse cotangent, but these three are the ones that are used most often. And so yeah, let's go ahead and get into it. So I want to emphasize this inverse thing. So for example, hopefully we realize this: the sine of pi over 3. First of all, that's the sine of 60 degrees. I've done this in a previous video. And the answer to this, and again, refer to that video if you're not sure where that comes from, is going to be square root of 3 over 2. Okay. So here's what we get. We get an x value of pi over 3 and a y value of square root of 3 over 2. That's our x and y value. So without doing any calculation, we can immediately say this, that the inverse sine the inverse sine of square root of 3 over 2 is pi over 3. Okay, x and y are interchanged. Right? Notice for regular trig, the angle goes in. This is an angle in radians. Angle goes in, and then a ratio of two sides comes out. For inverse trig, a ratio goes in and an angle comes out. It's what angle has a sine of this. That's how we think about inverse trig. What angle has a sine of the thing that I'm pointing to there? 60 degrees is pi over 3. Okay? Good. Now, so, that's how we can do a calculation like that. Now, very quickly, the restricted ranges for the inverse trig functions. So if we look at a regular sine graph, regular sine function looks like this. Well, to an extent, it's prettier than what I got here. But basically, in order for this thing to be invertible, it's got to be 1 to 1. Clearly, this thing does not pass the horizontal line test. However, if we cut the function off here at the minimum, and then cut it off here at the maximum, and then just go from the min to the max, in other words, just this orange bit here. If we just consider the orange bit, this passes both vertical and horizontal line tests, and this happens from the max to the min, which is minus pi over 2 to pi over 2. Okay, so these are the x values of regular sine. Okay, so that means that the y values of inverse sine, if y is the inverse sine, then y has to be from minus pi over 2 to pi over 2. Which, if we think about our little angles, that means that we're only going to be sketching angles from here to here. Minus pi over 2 points straight down, positive pi over 2 points straight up. Minus pi over 2 to pi over 2, that goes through 0. 0 is here. So we're talking about quadrant 4 and quadrant 1 for the inverse sine. Okay. Inverse cosine, let's take a quick look at that. Inverse cosine. So first, here's a regular cosine function. Let me plot that. Plot a regular cosine function. Cosine starts at the maximum there. There's one period of cosine, and then I can do another period this way. Okay. Now, first of all, notice if I try to go from minus pi over 2 to pi over 2, that's not allowed. Because that's still not invertible. It doesn't pass the horizontal line test. If I go from minus pi over 2 to pi over 2, then I'm not invertible. So I have to do something else. And so if we take a look, the maximum is supposed to be here. If I go from the max and then down to the min, similarly to how we did with the inverse sine, if I go from here to here, then this chunk once again is invertible because it passes the horizontal and vertical line test. And so this happens at x equals 0 and x equals pi. And so these are x values of regular cosine. So for y equals the inverse cosine of x, the y value of the inverse cosine has to be from 0 to pi. And if we think about our little sketches, sketching little angles, that means we're talking about from 0 to pi. So we start here and here. That's quadrant 1 and quadrant 2 is our restrictions for the inverse cosine. Lastly, for this video is the inverse tangent. And I do want to just point out that there are multiple valid ways to restrict an inverse trig function's range. And here I'm drawing a regular tangent function. So tangent looks like this. It's got asymptotes at plus or minus pi over 2 because tangent's y over x. And so tangent's going to be undefined wherever x is 0, wherever the denominator is 0. X is 0 at plus or minus 90 degrees. So here's pi over 2. Here's negative pi over 2. And once again, you know, if I keep plotting tangent curves, or tangent periods rather, then, you know, these all together do not pass the horizontal line test. But if I restrict myself to just a single period, so just between these two asymptotes, if I just look at this region, and this region only, one period by itself does pass the horizontal line and vertical line tests. It might not look like it passes the vertical, but it does. And so for this reason, the inverse tangent is going to have a restricted domain from minus pi over 2 with parentheses to pi over 2. Once again, because the tangent is undefined at pi over 2. Okay? Good. So there's that. And now let's go over just a couple more little quick examples for calculations' sake. Let's say we have the inverse tangent of 1, for example. Okay? Well, inverse tangent, I want to think about the restricted range, is going to be from minus pi over 2 to pi over 2. So that's going to be quadrant 4 or quadrant 1. And the number inside is positive, so it can't be quadrant 4 because tangent is negative in quadrant 4 because y is negative in quadrant 4 and x is positive. So it has to be quadrant 1. So we want the quadrant 1 angle that has a tangent of 1. So the tangent of something has to be 1. That means, well, definition of tangent is y over x. Y over x has to be 1. If y over x is 1, that means y and x have to be the same. So if y is 1, x is 1. So we're talking about this triangle. Y and x are both 1. That means this one has to be square root of 2 if we use Pythagorean theorem, right? 1 squared plus 1 squared. 1 plus, 1 squared plus 1 squared is 1 plus 1, which is 2. 2 is r squared, so r has to be square root of 2. That's the 45, 45, 90. So here's 45 degrees. Here's 90 degrees over here. So then the angle has to be 45 degrees, or pi over 4. And that problem is finished. Okay. We could also do stuff like the inverse cosine of -1. Inverse cosine of -1. So, just it's like I was saying before. It's equal to something. Take the regular cosine of both sides. These are inverses. Cosine of inverse cosine goes away. We get -1 equals the cosine of something. So it's like, what angle has a cosine of -1? Once again, use definitions. Okay. Cosine y equals -1. That means x over r has to be -1. That means that x has to be negative r. It means x has to be negative. If x is negative r, we're talking about something that points this way. That's 180 degrees, which is pi. Okay, so the answer is pi. And once again, just to remind you, in inverse, the range there, 0 to pi. So we're good to go there. One more. Let's do inverse sine. Inverse sine of -1/2. Well, it's some number. And just like we did before, if I take the regular sine of both sides, regular sine, this is how we get stuff out of an inverse sine or out of regular sine. You operate with the inverse. Sine of the inverse sine, we get sine y equals -1/2, but be careful. There is the restricted domain, or I'm sorry, restricted range, restricted value on y. So y has to be between minus pi over 2 and pi over 2. Okay, so that's going to be either quadrant 4 or quadrant 1. And it's negative. It's negative, so it can't be quadrant 1. It has to be quadrant 4. So we want a quadrant 4 angle. And we know the definition of sine is y over r. So y over r is -1/2. So quadrant 4, y is -1. Y is -1. R is twice that size. So -1, 2. So ask yourself, what triangle is that? What angle is this? The triangle is the 30, 60, 90. Here's square root of 3. The angle inside is 30 degrees. Except it's 30 degrees below the x-axis, not above. So that means the angle is -30 degrees, which is -pi/6. Okay, so that's that. So there we go. Basically a full inverse trig review, complete with examples, complete with background, what is invertibility and all that stuff. Good.